All right, recorded is rolling. It is Tuesday, December 13th. We're gonna do the questions of this midterm review. I gave you guys this page a few days back. There's about 100 questions here. You guys remember the midterm is open notes. Friday, Monday, we went over that PowerPoint that was posted to Google Classroom. Right now we're gonna switch over and look at all these conceptual questions. Okay. So let's get going here. All right, first question. When you look at the speedometer in a moving car, you can see that car is what? What does the speedometer tell you? It tells you how fast the car is going at that instant. Okay, is that called instantaneous speed, like instantaneous velocity? Right? Those would be good choices. Okay. What if you saw a multiple choice option for average velocity? That's not what that refers to, right? We almost never talk about average velocity in class. Average velocity is like total distance over total time. You go on like a 200-kilometer road trip, and sometimes you're at the gas station, sometimes you're on the road, right? And you divide those out, right? That could be like an average velocity situation. But instantaneous velocity, that's what the speedometer needle points at, tells you what's going on in that instant. And it's also the values that feed into these equations. Okay, this is an instantaneous velocity. This is an instantaneous velocity. Right? Their velocities at certain instances. Okay. Yeah.
For the study guide, are we allowed to write our answers on the note paper?
Yeah. Take notes however you want. Yeah. Train travels 6 meters in the first second, 6 meters in the next second, 6 meters in the third second. Okay. So what is the velocity of that train? Does it look like it's going 6 meters per second? Okay. I think the velocity would be 6 meters per second. But that's not actually the question here. The question is, what is the acceleration of the train? What's the answer to that question? Yeah. Zero meters per second squared. Because you guys know that acceleration is a rate change of velocity. And there's no change in velocity here. It's just going at constant velocity. Anytime you have constant velocity, that's zero acceleration. Car starts from rest, and after 7 seconds has picked up to 42 meters per second. What is the acceleration? So, okay, so some of you guys are saying 6 meters per second squared. Right, awesome. Right, so 6 times 7 could be 42. If you want some kind of framework to help you think about this, navigate this, could you say V final equals V initial plus AT? Okay, so say we're going up to 42 meters per second. This is from rest, so that's 0 meters per second there. Okay. And then see, solve for acceleration. This all happened in 7 seconds. Divide 7 over exactly what you guys said, 6 meters per second squared. Boom, just like that. As an object falls freely in a vacuum, let's see, does its speed increase? Yeah. Or you could say the magnitude of its velocity increases. That would be a good choice too. Does its acceleration increase? No. We're going to call its acceleration constant. Okay. So acceleration is constant all the way down. Let me flip my screen. I'm going to do this just a few times today. Really just mostly focus on one particular slide that you guys have seen in the last few days. Okay. You guys remember this here? Drop a ball from the edge of a cliff. Right? So a lot of info on this table. So you got a column for time. So here's time taken 1 second at a time. Right? Goes up to 5 seconds of falling. Okay. And then, let's look at this whole table. How about that? Right. So you guys see how the acceleration is constant all the way down? So we're rounding a little bit, but let's call it 10 meters per second squared on Earth. Right? That's constant acceleration, which means that its velocity picks up 10 meters per second per passing second. So velocities go 10, 20, 30, 40, 50 meters per second. So it picks up at a constant rate. The constant rate is acceleration. That's what's constant. Okay. How about this? Look at its displacement versus time. You guys see during the first second, it only fell 5 meters. But then the next second, it picked all the way up to 20 meters of how far it fell. Okay. Woo. All right. That's a huge jump. Hey, do you guys think that every single successive second it picks up more falling distance than the previous second of falling? Okay. I think so. Right. In fact, if you graph x versus t on a graph, you get, oops, I skipped too far. You get this parabola right here, right? X versus t, it's a parabola shape. So every second that passes, it falls further than the previous second. You guys see that? Right here. All right, you guys can do that. All right, let's switch back over to, let's see. Okay. Ball tossed vertically upward rises, reaches its highest point, and then falls back down to the starting point. Okay. During this time, the acceleration of the ball is always, okay, let's do magnitude and direction. What's the magnitude of the acceleration on Earth always for free fall? It's called 10 meters per second squared. And what is the direction of that acceleration? It's always pointed which way? Towards the Earth, or you could say down, right? So anything in free fall near the surface of Earth, I'm going to say is always accelerating down at 10 meters per second squared, regardless of its direction of velocity. If it's going up to the side, thrown down, right? It's always 10 meters per second squared downward. Isn't its weight always downward? And forces cause accelerations, which skipping ahead a few chapters on that idea. That it's a trigger. So always down. Ball is thrown straight up. At the top of its path, its instantaneous speed is what? 0 meters per second. Right at the top, 0 meters per second. Okay. Follow-up question. Same scenario, ball is thrown straight up. At the top of its path, its acceleration is what? Yeah. 10 meters per second squared downward, right? So as soon as it leaves your hand to the point that you catch it again, it's in free fall, it's going down, it's 10 meters per second squared. A car accelerates at 2 meters per second squared. So I'm looking at the speedometer needles. It's picking up 2 meters per second every second. It's going 6, 8, 10, 12, 14 meters per second. The car starts from rest. How much time does it take to pick up to 20 meters per second? What do you guys say? Yeah.
10 seconds.
I think 10 seconds sounds like a great answer. 10 seconds. Okay. And if you needed a framework to help answer that, I think the same equation we just used a few minutes ago. Let's try it again. VF equals V naught plus AT. Okay. So we're going up to 20 meters per second. Starting from rest. Okay. And we're picking up 2 meters per second every passing second. It's about 2 meters per second squared. Okay. Yeah. Divide that 2 meters per second squared down. Got a time of 10 seconds. Boom. Okay. Freely falling object is equipped with the speedometer, so we're getting its speed every second. How much would the speed reading increase every second? 10 meters per second, right? And we were just looking at that on that table in that PowerPoint too, right? Assuming we're on Earth, we're ignoring air drag, the whole deal. A freely falling object starts from rest. If it's fallen for 6 seconds, it will pick up to a speed of what? Did I say 60 meters per second? Okay. Which here, I'll flip over again. Because that would have been the next row on the table if I threw on another row. Okay. So I only went up to 5 seconds here, but what if I threw in a 6 second? You guys see the velocity 10, 20, 30, 40, 50. The next row would be 60 meters per second. Okay. You use that equation. We've been using it a few times. Let's see, switch back over here. A ball is thrown into the air at some angle. Ooh. So now we're on to projectiles. Okay, so let's get a projectile going. Ball, some angle. Make a nice smooth parabola shape. Okay, nice smooth parabola. Okay. At the very top of the ball's path, this is the question on your page. Okay. Very top of the ball's path, what can you say about its velocity? I'm thinking of maybe a couple of facts I could take. Okay. How about its direction? What is the direction of the velocity at the very top? It's entirely what? Horizontal? Okay, isn't it entirely horizontal right at the very top? Okay. How about this? At the point that you threw it, when you threw it at some angle, maybe kind of up and to the right, okay, could you split that into components and say the amount to the right is called v sub x, and the amount upward at that moment is v initial in the y direction? Of course, that immediately starts changing as gravity's pulling it downward. But the vx part, does that stay the same all the way throughout the flight? Is that vx right there? The same thing as this vx right here? Yeah, right? Right, same thing. How about this? Does the ball slow down on the way up and then speed up on the way down? So it has minimum speed at the top too, right? Okay. So I'm thinking at the very top of the ball's path, its velocity is entirely horizontal, and its speed would be the slowest it's going. It'd be like minimum speed. Okay. A ball thrown in the air will never go as far as physics ideally would predict because, right? So we break out those projectile equations. Say I throw the ball into the air at some angle at some speed, and we do all the calculations. Say, oh, it should go like 55 meters, right? Then we go into the field behind the school and we actually try this experiment, and it always lands a little bit short. Why is it doing that? Why is it always landing a little bit short? Because
Air drag.
air drag. Yeah, that's the best answer right there. Air drag. Okay. Because all these equations we're ignoring air drag, and there's a good reason we're doing that. Because if you include air drag, the math gets really crazy. It's like post-calculus 3 math, but if you ignore air drag, it's just very simple parabolas, which is approximately, it's pretty close to it, so it's pretty good. Airplane flying into a headwind loses ground speed. Airplane flying with the wind gains ground speed. Okay, here, let me sort of get us a setup here. That's just the premise, right? So I've got this airplane. Let's have this plane flying straight north. So it's directed north, its engines are blasted north, and it's flying straight north. Okay. Let's say that its engines relative to the air around it can power it at like 40 meters per second. So that's what I'll have, 40 meters per second. It's going. Okay. Now, that's if the air is not moving. Suppose there's no wind, right? Everything's just still, right? Relative to each other. The plane is just going north at 40 meters per second. Okay. Now, what if the wind is going also north at say 30 meters per second. Okay, so 30 meter per second wind straight north. And some guy down on the ground points a radar gun up at the plane. How fast does it look like the plane is going? It's at 70. 40 plus 30 is 70. Right. Now that's not the question on your paper, but this is part of the premise. Okay. What about this? What if the wind is blowing straight back towards the plane at 30 meters per second? Now is the plane going really slow compared to the ground? 40 minus 30 could be 10 meters per second. Add those tip to tail. Okay. But here's the question that's actually being asked on your page. What if there's a crosswind? So the wind's blowing straight east, for example. I'll have this at 30 meters per second. Okay. All right, so now if you're down on the ground and you point a radar gun at this plane, how fast does the radar gun say the plane is moving?
50 meters or something?
50. How'd you know that?
I just saw it as a 3, 4, 5 triangle.
It is a 3, 4, 5 right triangle, isn't it? Right. Yeah. So you do Pythagorean theorem. Notice I connected these vectors tip to tail, although the wind is blowing east everywhere. But this is a good physics process, tip to tail vector connection. So you get the resultant, which is 50 meters per second. You guys could do c squared equals a squared plus b squared, Pythagorean theorem. If these numbers weren't very convenient 3, 4, 5 right triangle. Okay. That's like that number right there. Okay. It's like 40, 30. That makes this 50. Okay. 3, 4, 5 proportion. Okay. So the answer is that the plane actually goes faster. Its ground speed increases because of this 90-degree crosswind. Its ground speed increases. All right. You guys good? Let me throw in my own question. Does anybody remember or know how to get this angle right here? Because the plane is pointed straight north, but it doesn't actually move straight north. It actually moves kind of northeastish. At what angle? So it's about 37 degrees for this 3, 4, 5 geometry. Okay. And you can get that by doing, here's one way to do it, inverse tan of 30 over 40. You do that, right? All right. What is the resultant of a 3-unit vector and a 4-unit vector at right angles to each other? Oh, we kind of just did that, didn't we? The 5 units. Right. Those units could be, well, anything that's a vector. Right? So it could be meters, could be meters per second, could be meters per second squared, could be newtons. Okay? Could be just anything that describes a vector. Okay? Got a 3, 4, 5 right triangle they're talking about. Okay? Pythagorean theorem. When in orbit, a satellite such as the space shuttle, could you say the space shuttle is simply a projectile? Right, that's just going so fast it's falling around the curvature of the Earth. Right? So maybe it's following a circular or an elliptical path rather than a parabolic path. But you just call it a projectile, right? Okay. It's just a really fast projectile. You guys could say it for space shuttle. I think that question showed up before on a Kahoot. After a cannonball is fired into frictionless space, the amount of force required to keep it going equals how many newtons? Is that the Voyager 1 spacecraft question? Voyager 1 been going since the 1970s. Let's keep it going. Just inertia, right? Which is not a force. So zero force, 0 newtons of force. Okay, you guys are saying 0 newtons of force? Okay. Out in the middle of deep space, it's just going just because of inertia, right? Inertia keeps it going. If the force of gravity suddenly stopped acting on the planets, they would. So let's get this going. I got a sun. I got an orbit for a planet. It's a planet right there. Okay. Okay. This planet's just going around. Okay. Zoom out a little bit here. Okay. And then right at this moment, suddenly you turn the gravity off. Does this planet make a random 90-degree turn and then just fly straight away from the sun? No. Okay. Does this planet continue on in the straight line path tangent to its original orbit? Yeah, that's what it does. So if gravity turns off, right there, it's just going to keep going in a straight line, tangent to its orbit. Right? Here's that. Hey, is that also true for what if you put a ball on a string? What if instead of gravity force, what if it's a tension force on a string, and the ball's going around, and you cut the string? Does the ball also go tangent to that orbit? Yeah. By the way, tangent to its motion is like this. If you take your pencil and put it like flush to the curve, just keep going in that direction. That's a Newton's first law of motion concept. A sheet of paper can be withdrawn from under a container of milk without toppling the if the paper is stirred quickly. Why? Do you guys remember? Did I show you guys a Paul Hewitt demo with the tablecloth trick? Okay, yeah. If you missed that day for whatever reason, put all the Paul Hewitt demos in a folder back on, I think, the first week materials. But yeah, he did this trick where he put a bunch of dishes on a tablecloth on a table, right, and then jerked the tablecloth really fast, and all the dishes pretty well stayed in place. That's because all those dishes, in this case, the milk carton, has a lot of what starts with an I? Inertia. So you care about that, right? A lot of inertia. Mass could also be a good option. Mass, inertia. I think inertia would be the best. What if you saw an option for weight or friction force? Those you wouldn't care about so much, right? Even though weight's proportional to mass, but that would not help very much. But in fact, it has so much inertia. That's what you care about staying in place. The force required to maintain an object at constant speed in free space is how many newtons? Zero newtons. That's the Voyager 1 spacecraft question again. Equilibrium occurs when? Okay. So the short version answer would just be the sum of the forces goes to 0 newtons, right? The sum of the forces is 0 newtons. Okay. Now you can get a little bit more specific. What if you introduce a Cartesian system and you break those forces into components? Would it also be true that the horizontal components zero out and also the vertical components themselves zero out? Yeah, those would all be true. Those are all true statements. Okay? A few questions coming, I think like 3 or 4 questions from now, I'll draw a picture for that. So hold on to this idea because it's coming up again pretty soon. Okay? So the forces zero out, but also along each particular axis, x-axis, y-axis, the components of those forces also individually zero out. Right? And then recently, just in the last couple of weeks, we added one more condition for equilibrium. We said, well, the torque also goes to 0 Newton meters for torque. That was a recent addition to that. Next question. Girl whose weight is 500 newtons. Ooh, pause right here. What is her mass approximately in kilograms? Are you thinking 50 kilograms? Right? 50 kilograms weighs about 500 newtons, surface of Earth. Right? Is in the middle of a bar supported by 2 vertical strands of rope. What is the tension in each strand? Okay. So I think it's a pretty straightforward version of this, but let's do it. Okay. So got a bar. Oops, let's focus here. I have a stick figure. Out in the middle here. And let's see, she weighs 500 newtons. Let's go 500 newtons. And there's these 2 vertical strands of rope at the ends. Okay. You're gonna tell me, what's the tension in each strand? Is it 250 newtons? I think it's 250 and 250 newtons. Okay. Now this is something you guys could have answered like a few months ago. Say, okay, get that right. The principle is this: the sum of the forces is equal to 0 newtons. We could specify the y direction. So 250 up, balances 500 down, equilibrium. Okay. Now you know that she's right in the middle. Now here's a little bit tricky addition to this. What if she's not right in the middle? What if she shifted a little bit to the right? Could this be like 200 and 300? Or even like 100, 400 maybe, right? Depending on where she is. It depends on her exact location. Okay. So if you want to get the exact tension, individual tensions, and she's not right in the middle, you guys remember you have to bring in this concept too. The sum of the torque goes to 0 Newton meters. Right. Review this with you guys real quick, because this is the day 2 of a 2-day lab you guys did with torque. You guys remember this? You had a couple of spring scales. You guys had one lab weight. You guys had a meter stick. Same thing as this, right? Okay. So I can pick any point as the pivot point. Suppose I take this point right here as the pivot. Okay. From this point of view, it looks like half the length of the beam times 500 newtons is causing a clockwise torque, and the full length of the beam times 250 newtons is causing a counterclockwise torque, and those two are exactly zeroing out. Okay. And then if she was not at the center, then you could use this method to figure out those tension. Okay. So that's a recent update to an old idea. You guys good with that? Okay, next question. Friction is a force that always acts which direction? Is it opposite of the motion? Yeah, it's opposite of the motion, right? Friction is going to oppose the motion. Like two surfaces sliding past each other. What is the maximum resultant possible from 2 newtons and 8 newtons? Right. Oh. So suppose I got an object and I put some forces on it. Okay, I've got an 8 Newton force and maybe like a 2 Newton force. Okay, they could conspire together, they could be opposite of each other, or they could be at right angle, or they could be like these angles. Okay, you can get all different options. So let me draw these out for you guys. I'm going to connect these tip to tail. Let's go 8 newtons and 2 newtons. Or what if you do it this way? 8 newtons and 2 newtons. Or what if you do it this way? 8 newtons and 2 newtons. Okay. You guys see how I've connected all these tip to tail? Okay. And then I can get a resultant by going from the tail of the first one to the tip of the last one. What's the net force on that first example? 10 newtons. What's the net force on the second example? 8 minus 2. Do you guys see 6 newtons? Right? Net force. Okay. How about this third one? Ooh, could I do a Pythagorean theorem? The square root of 8 squared plus 2 squared. That looks like probably about 8.25 newtons net force, right? Pythagorean theorem, let's kind of go up to it. So it looks like the maximum is just going to be 10 if you just had them both in the same direction, conspiring together. You guys got that? Here's the picture. I just promised you guys a few questions ago to draw, guys. A 100 Newton lantern is suspended from a pair of ropes, 120 degrees between them, or you could call it 60 degrees to the vertical. What is the tension in each rope? Okay, so this is a 2-dimensional force equilibrium question. So I'm actually going to start with a Cartesian system. Got my y-axis parallel to gravity. Got my x-axis, say parallel to the ground. X, y. Okay. Okay, here's where all the ropes are coming together. Let's have a 100 Newton lantern. So I'll do a down force vector. This is a force vector of 100 newtons. Yeah, maybe I could, I guess I could like draw a lantern for you guys, right? So, oh, shiny. Okay, and then there's a couple of ropes that are 120 degrees from each other. Try to get that pretty close in my picture here. That's exact. I think it's pretty close. About like that. Okay. Now, guys, if that right there is 120 degrees, which they said, by the way, you could also call this 60 degrees if you like. Okay. Then what is this angle and what is this angle? Is this 120 degrees? And this is also 120 degrees to complete a circle of 360 degrees? Hey, is that completely symmetrical? Yeah, I think so. Let's change out the story a little bit here. Okay, let's get rid of the gravitational forces down on the page. What if there's three guys playing a three-way tug of war with they tie some ropes together. We're up in a helicopter looking down, aerial point of view. Okay. Okay. And does this look completely symmetrical? And if this guy's pulling with 100 newtons, what do you guys think each of these guys pulling with? Think 100 newtons also? I think this is 100 newtons right here, and this is 100 newtons right here. Okay. So I think this question was trying to gear you towards like that point of view. Say, oh, well, based on symmetry, it's got to be that. Okay, okay, back to that. Here's what I want to do with this though. I want to get a bit more granular because I can say that the sum of the forces in the x direction is 0 newtons, and the sum of the forces in the y direction is 0 newtons. Okay. This by the way, looks really similar to one of the PowerPoint slides we did over the last couple of days, and also one of your labs way back in the day when you guys had some spring scales. You guys did a version of this. Okay. So since I have this Cartesian system established, can I break these two guys into components? Say, well, this guy's pulling kind of up and kind of to the left, and this guy's pulling kind of up and kind of to the right. Just that a little bit, but I see the idea. I see some right triangles going on there, right? They're doing this right. Let's go like right there. Okay. So that first condition, sum of the forces in the x equals 0. Do you guys see how that balances with that? Right, so that to the left equals that to the right, so equilibrium from that point of view. Okay. How about the y direction goes to 0? You guys see that this component and this component together have to balance out with 100 newtons down? So this needs to be 50 and 50. Okay. Hey guys, what is cosine of 60 degrees? Is that 1/2? Cosine of 60 degrees is exactly 1/2. Is that? Remember that? Okay. And if that's true, let's say starting from knowing what the answer is, that this is say 100 newtons. 100 newtons times cosine of 60 degrees would be 50 newtons. The same is true for this guy. Another 50 newtons. 50 plus 50 balances with this 100. Okay? You guys remember all that? Okay, so a little extra bonus review on that one. Next question, which has more mass, a kilogram of feathers or a kilogram of iron? And you guys say that they're both 1 kilogram. Right? So it's the same mass. Right? Same mass, same inertia, same weight, maybe different densities and different volumes, but it's just the same mass. Accelerations. Now, the first few weeks of this class, we said what acceleration is. We could quantify it as the rate change in velocity. But then we started thinking about it. Hang on. I remember Newton's first law of motion says nothing ever wants to accelerate. So if something is accelerating, that's because there's a what acting on it. Force. Yeah, force. That's the answer to that one. Accelerations are produced by forces. How does the acceleration of an object change in relation to its mass? Okay. So this is a Newton's second law type question. Guys remember Newton's second law of motion? Acceleration is force on mass. Or maybe I should really say this, a net force. Like if there's multiple forces, you find the net force first, and then divide by mass, they'll tell you the magnitude of the acceleration, but also the direction of the acceleration. True? Okay. Here, give you guys an example with this one. Suppose you got a ping pong ball, a tennis ball, and a bowling ball. So increasing mass from left to right. Okay? And we put the same force on each of these guys, the same force. It was like 20 newtons of force. Pew, pew. The same force, right? Different masses. Is this going to accelerate differently? I think so. Okay. Now this question says, how does acceleration change in relation to mass? Let's make a graph out of this. Acceleration meters per second squared as a function of mass in kilograms. Okay. So this could be the tennis, the ping pong ball, the tennis ball, the bowling ball. Okay. So for the same force, isn't the ping pong ball going to have a huge acceleration? The tennis ball can maybe kind of medium, and the bowling ball is going to have, it's just going to move a little bit, right? Do you guys see an inverse relationship? Inverse relationship? I think that's the answer to that question right there, right? And just like the formula for that graph, there's an inverse relationship between acceleration and mass. When an object reaches terminal velocity, Now, terminal velocity, you guys know you have to account for air drag. This is something's falling faster, faster, air drag picks up more and more, okay? Until finally the air drag balances the weight of the object, which means the net force goes to 0 newtons, which means the acceleration becomes what? 0 meters per second squared, okay? Terminal velocity, there's 0 acceleration. Okay? So it's still moving, it's moving really fast. It's just constant velocity all the way down to the ground in equilibrium. Oh yeah, go.
Say again, the acceleration is what?
0. 0 acceleration. A book weighs 4 newtons when held at rest in your hand. What is the net force on the book? Let's draw this out. Book. Right there. The weight is equal to 4 newtons. Okay. Now, if it's held at rest, is the force from your hands also 4 newtons, but just upward collective force, I guess, right? Okay. So what's the net force? 0 newtons. See, 0 newtons net force. Girl pulls 10 kilogram wagon with 20 newtons of force. What is the acceleration? Newton's second law of motion. Looking at 20 newtons of force on 10 kilograms. That 2 meters per second squared. 2 meters per second squared, right? Guys see that? Force on mass is acceleration. An object has constant mass. A constant force produces a constant what? Here, I'll narrow it down to a couple options for you guys. Would that be a constant velocity or a constant acceleration? And you guys say constant acceleration, right? Constant acceleration. Right? It's a constant force and a constant mass, so it's a constant acceleration, which is a changing velocity, but the rate change of that velocity, acceleration, is constant. Pressure. You guys ever pump up any bike tires? Right? You guys have an American bike pump? What's the unit on an American bike pump for pressure?
PSI.
PSI. Isn't that like pounds per square inch? Ooh, pounds is like a force. Square inch is like an area, right? And then in this class, since we almost exclusively use a metric system, I would call that newtons per square meter, which is pascals. Right? 1 newton per square meter is 1 pascal. If the force acting on a cart doubles, what happens to the cart's acceleration? Well, if you double the force, is the acceleration also going to double? You guys think? Right? I think it would. Hopefully you can see that from the variables, but if not, can you guys just make up some numbers and try it out? Right? Like we have one wagon being pulled with some force already. So what if you double that force to like 40 newtons? That's doubling the force, right? Same wagon. You guys see 4 meters per second squared? Okay. So if you double the force, you're going to double the acceleration. We've done quite a few of those proportional type questions in this class. Suppose a cart is being moved by a force. If suddenly a load is dumped in the cart so that the cart's mass doubles, now what happens to the acceleration? Mass doubles. Maybe it's going to say, if this mass doubles for the same force, like pushing a cart, same force, mass doubles, the acceleration is going to be half as much. Just like that. Right? Again, if you want to see a number, example, okay, let's start with this as like the base example. Okay. What if I double the mass of this cart to like 20 kilograms? So I'm doing the same 20 newtons, but now it's on 20 kilograms. I'm starting to fill up the cart. It's now going to be 1 meter per second squared, just like that. Okay. So here's the original example. Okay. Here's doubling the force produces double the acceleration. And here's instead, leave the force the same but double the mass, you're going to get half the original acceleration. Okay. Boom, boom, boom. 20 Newton falling object, which, by the way, I guess would have a mass of about 2 kilograms. It's about 2 of these. Okay. So 20 newtons falling object, encounters 4 newtons of air resistance. What is the net force on the object? 20 down, 4 up. What's the net force? 16 newtons, right? Do one more thing with you guys with that. Okay. So this is 2 kilograms. Therefore, it weighs 20 newtons. Okay. Say it runs into 4 newtons of drag force. Okay. Guess the net force, 16 newtons. Okay. If you let that act on a mass of 2 kilograms, guess the acceleration would be 8 meters per second squared. So it's still accelerating, just not at the full rate of free fall because there's a little bit of air drag. 6 newton falling object encounters 6 newtons of air resistance. What is the net force? 0. Yeah. Hey, I think that would be terminal velocity. So it's still moving really fast. Okay. Wouldn't have any air drag if it wasn't moving really fast. Okay. But it's just not picking up speed anymore. High school student hits a nail with a hammer during this collision. Is there a force on the nail? Yeah, there's a force on the nail. Is there a force back on the hammer? Yeah. But which force is bigger, the force on the nail or the force on the hammer? For every force, the same. For every force, there's an equal and opposite reactive force, right? This is Newton's third law of motion. Now, Newton's third law of motion, you need 2 different objects interacting with each other, right? And then the force from one to the other, well, it's the same both ways. Right? They have to be equal and opposite force pairs. As a ball falls, the action force, for example, could be the Earth's mass pulling on the ball, creating a gravitational force. Wait, okay. What is the reaction force? So let's see, the Earth pulls on the ball. Does the ball pull on the Earth?
Yeah.
Yeah, in fact, that's the answer, isn't it? Right, that's the reaction force. Okay. Do they pull on each other with the same force? Yeah, same force, same force. Okay. Same force both ways. Okay. If you saw a multiple choice option for the air drag, would you pick that one? It's not the air drag. That's a third object. We don't care about that. Okay. So even at terminal velocity, right? So Earth pulls on the ball pulls back up on the Earth with the same force. Ooh, next couple of questions. Got a pair of questions here about this unfortunate bug. Splatters against the windshield of a moving car. Compared to the force of the car on the bug, the force of the bug on the car is what? The same. It's Newton's third law. Same force. But here's the follow-up. Compared to it says deceleration. Maybe we could think of like the change in motion of the car. The change in motion of the bug is much what? Much greater, right? Because the car barely notices, right? I mean, even though the force is the same, right? Maybe the car was going like 60 miles an hour, now it's going like 59.99 miles an hour, right? So slows down a tiny bit, you would hardly even notice, right? But from the bug's point of view, it was flying its own speed, and then bam, it was a huge change of speed in a very small time interval. Right? So how is this consistent with Newton's laws? Well, acceleration is caused by a force acting on the mass. Now they said the word deceleration, but you just call it like negative acceleration or something, right? Okay. So it's the same force. Different masses produce different accelerations. Right? Little tiny bug is a tiny mass, which results in a huge acceleration. Large car has a small acceleration. Large truck and a small car traveling at the same speed have a head-on collision. The car to undergo the greater change in velocity will be the, you guys said the small car, right? The smaller mass results in a larger change in motion. Right? I'm thinking the small car is going to undergo a greater change in motion. Which vehicle would you be safer driving in? I think of a large truck, you'd be safer driving in. 2 people pull on a rope in a tug of war. Each person pulls with 400 newtons of force. What is the tension in the rope? I say 400 newtons, right? 2 guys are pulling 400 newtons. The overall tension in the rope is still 400 newtons.
But why?
What's that?
Why?
Here, let's take a look at this. So, okay. Couple of guys pulling. Okay. So maybe this guy has a spring scale. Throw on a spring scale right here. Okay. Maybe this guy throw on a spring scale. Hey, maybe we could like throw on a spring scale right in the middle. Okay, the spring scales could tell us what the force readings are, right? Okay. So if this guy pulls with 400 newtons of force to the left, okay, this bit of the rope is pulling back with 400 newtons to the right, okay, to like zero out that spring scale, or well, not zero it out, but zero net force, right? So it's reading like 400 newtons. Okay. This guy, same story over here. He's pulling to the right with 400 newtons. So the rope pulls back with 400 newtons. Okay, so there's zero net force, so it's just hovering in place. If you threw a spring scale right in the middle, that spring scale would also read 400 newtons. This guy's pulling this way, 400 newtons. This guy's pulling this way, 400 newtons. Right? Or how about this? What if you replaced one of these guys with a tree? Okay, throw the rope around the tree. Okay, so this guy's pulling with 400 newtons. The tension in the string, tension in the rope is 400 newtons all the way, and then the tree has to pull the other way with also 400 newtons. Okay, so there's 400 newtons everywhere. Table tennis ball launcher is fired. Compared to the force on the ball, the force on the launcher, is that the same force? It's the same force. That's just Newton's third law all over again. Okay. That's a good segue to this next question. Same scenario. Table tennis ball launcher is fired compared to the impulse on the ball, the impulse on the launcher. Okay. So I'm gonna just draw a cannon and a cannonball. It's the same idea, right? Okay. So there's pow, some explosion here. There's a force this way. There's a recoil force this way. It's the same force. Same force. Right. Now, impulse. You guys remember impulse is a change in momentum? And there's a couple perspectives on that. You could call that mass times change of velocity. That's fine. Okay. But where do you get that from? You get that from applying a force for some time interval. It's like an average force, but it's the idea. Force for a time interval. Okay. Now, we just established that the force is the same on the ball and the launcher. And the time interval of that force is also the same. So is the impulse the same? It is. That's the same. That's the same. That's got to be the same. Right? We can go another step here. Now, those two objects have different masses. Right? The ball is a little tiny mass, and the launcher is a huge mass. So they have different changes in velocity. Right? The little tiny mass, pew, takes off. The big mass, the launcher, recoils just really slow. Okay. Right, you guys that? Which I think is the next question. Yeah. Okay. They said a cannon recoils from launching a cannonball. So same idea. Okay. If the speed of the cannon's recoil is small because the cannon has so much what? Mass. Yeah. So much mass. Gives it so much inertia. Okay. Large mass results in a small change of velocity. For the same force, same time interval, same impulse. Okay. Different masses, different velocities. Okay. Let's just do these last few right here. A piece of putty moving with 2 units of momentum strikes and sticks to a heavy bowling ball that had initially been at rest. Both roll off into the sunset with how much momentum? So this is an inelastic collision. Here comes this putty with 2 kilogram meter per second. Inelastic collision right there. And then they both roll off because momentum is conserved with 2 kilogram meter per second. Okay, so that's the answer to that question. But you know what I really wish I had thrown on here, but I didn't catch until I printed this whole thing out, is what if you replace the putty with a bouncy ball? So let's get a bouncy ball going. And let's bring this in also with 2 kilogram meter per second, but let's have it rebound at boing, like 1 kilogram meter per second, but in the opposite direction. Maybe I should like tag a negative sign on that, right? Okay. Do you guys know how much the bowling ball rolls off with? How many units of momentum? And it's not 2, it's 3. 3 kilogram meter per second. You guys remember this? I think we did this a few weeks ago. Right? If it bounces off, the boing, it transfers more momentum than if it slides stuck to it. Right? Because momentum is conserved for both of these. Okay? In the system, momentum is conserved. Okay. A 2 kilogram ball is thrown at 3 meters per second. What is the momentum? Well, momentum is mass times velocity. So 2 kilograms times 3 meters per second. Is that called 6 kilogram meter per second? Right? 6 kilogram meter per second. You just multiply mass and velocity. And last question on this side. In physics, work is defined as is measured in joules, okay? Is work equal to force times distance, right? Force times distance, right? I might say impulse is equal to force times time, and work is equal to force times distance. Okay, and then tomorrow we'll pick up at the energy unit, right? And then that's all these questions here. Okay. And so that is a good pause point today. We've got about a minute till the bell.